Now we'll look at the limitations of telescopes and how they can be overcome. The most obvious limitation of a telescope, familiar to everyone who lives in a city or a suburb, is light pollution. There are observing problems due to the Earth's environment. Light pollution is inevitable. It comes from the scattered light of all our cars, all our houses, all our commercial activity. And you can see in the photos on the left the difference between a suburban dark sky and a suburban bright sky. The Milky Way would be impossible to see, and it would be hard to see more than a few dozen stars under a bright sky. So light pollution is a fundamental limitation in seeing the sky. For this reason, telescopes are built in particular parts of the world. Here we see, located on a map, the places where the world's largest telescopes are being built. And you can see they're not in Europe, and they're not in Africa, and they're not in most parts of Asia or the continental United States. There's a large aggregation of the world's telescopes in the Hawaiian Islands on Mauna Kea volcano and down in Chile, and then a handful of other large telescopes. And that's because these are the best places to observe, which becomes clear when you look at a photo of the Earth from orbit at night to see where the city lights come. It's very obvious where the dark places in the world are. So you want to go to those dark places. But it's not just darkness or distance from civilization. Modern observatories have large amounts of complex equipment, so you can't be too far away from civilization or ports or airports or infrastructure, or you can't support a modern observatory. So it's not as simple as being in a remote place. Also, some remote places on this map, such as equatorial Africa, don't have any high mountains for clear, pristine weather and have a lot of rain or tropical weather. So you don't want to be there either. So there are various constraints. The United States, regrettably, is becoming a terrible place for observational astronomy at optical wavelengths. You can see that east of the Rockies and the Mississippi, pretty much it's a continuously lit zone. There are some scattered areas out west on the plains that are dark. You see that the northern part of Mexico is also quite dark. The island of Cuba is dark, but there's a lot of light on this map. And this is how things have changed since the 1950s. So you can see that over half a century or more, the industrialized and eastern part of the country has just become a sea of light due to large numbers of people. But it's also the population living very spread out, and there are hardly any rural areas free of light pollution. And that means a dark sky is becoming a rare thing to see. Many young people have never seen a dark sky, which is sad. Here's a truly dark night sky, seen from out on a desert, time-lapse photograph, where you're actually looking now at the southern sky, because this is the way the Milky Way looks from the southern hemisphere. It's more prominent than it is in the north. Those two fuzzy patches that can be seen on the top right are the large and small Magellanic Clouds. They're actually distant systems of stars, about 70 to 100,000 light years from the Earth. They're not visible in the north because they're simply too far south. So this is a beautiful southern night sky. The second aggregation of things that make astronomy hard are the turbulence caused by the Earth's atmosphere. Turbulence causes twinkling or blurring of the star images. On the left you can see a star viewed with a 2-meter ground-based telescope and the same star viewed from orbit with the 2-meter Hubble Space Telescope. The increasing sharpness is simply because of the absence of an atmosphere. The Hubble telescope looks through deep space. There is no air between it and these stars. And that blurring, that turbulence from the Earth's atmosphere is an unavoidable effect of our atmosphere. The atmosphere also absorbs most of the electromagnetic spectrum. So if we do want to look at wavelengths shorter and longer than visible light, we can only look at a very narrow window. From the ground, we can basically look in a narrow window from about 0.3 microns, or 0.3 times 10 to the minus 6 meters, up to about 1.2 microns. And then there's a slight transmission for slightly longer wavelengths, and you can see that schematically. But there's no transmission for ultraviolet, for X-ray, for gamma ray. Transmission improves again at very long wavelengths, and so radio astronomy can be done very well from the ground. We do now, though, have some solutions to some of these problems, and I'll talk about them now. Some of them are happening right here at the University of Arizona. A frontier technology is to use large telescopes and large detectors. The data rate for modern telescopes is huge, 20 terabytes a night for the Large Synoptic Survey Telescope. And the woman on the left is holding the Charge Coupled Device Array. Remember, CCD is the small detector or sensor in all digital cameras and iPhones. So this is a huge version of that same digital detector, a very high quality one that will be cooled with liquid nitrogen, so they can observe a huge swath of the sky with one click of the shutter. And essentially this telescope will look at the whole night sky visible to it from Chile every night or every 2 nights, and then do it over and over again. Also on the right we see the mirror that's going to be used at this telescope, and the people will give an obvious sense of the scale. This is a huge mirror. Mirrors this large wasn't thought were possible to cast, and now we are able to cast them. And they have to be light. So if you made a mirror bigger and bigger, it would get heavier and heavier, and it would bend under its own weight. The same problem a refracting telescope has as the lens gets bigger. The way to avoid it being heavier as it gets bigger is to make it a honeycomb, where essentially when you build the telescope, you pour molten borosilicate, which is a kind of glass, around hexagonal molds so that the molten glass fills the spaces between the molds, and then when the molds are eventually taken out, you have a honeycomb structure where it's mostly airspace, plus a thin faceplate that's continuous glass surface, only an inch thick. This technology has been used to make many of the telescopes locally, the ones that I've used in my research. Here's the Large Binocular Telescope on Mount Graham in Arizona. It's currently the world's most powerful single telescope. It has 2 8.4 meter mirrors, is equivalent to a single 12-meter telescope because both mirrors point at the same part of the sky. Here's a bird's eye view. These are the 2 largest mirrors ever made at the time they were cast. And here is our future new telescope, which is the Giant Magellan Telescope. This is a schematic. That telescope is just being built as we speak. And you can see each of those mirrors inside the dome is an 8.4 meter mirror. And so you can see you have 6 of them in a pattern around a central one. So 7 8.4 meter telescope mirrors in an enormous building to being built in Chile, which will be the world's largest telescope. And it all happens right here in the football stadium.
Located underneath the east side of the stadium, the Stewart Observatory Mirror Lab can brag about making the largest telescope mirrors ever.
The Giant Magellan Telescope is the next step to achieve a 25-meter telescope aperture with 7 of these segments. And each of the segments is the biggest mirror that has ever been made in the world. Astronomers always want to build bigger telescopes. You get 2 huge advantages from big telescopes. One is you're more sensitive because you're collecting more light, you can see fainter objects. But the other thing you get is sharper images. The bigger the telescope, the sharper the image you can get.
With so many stars and so much data, each piece of glass the lab produces has to be within 1/millionth of an inch to perfection. Polishing scientist Buddy Martin uses a complex procedure, including a laser, to measure the surface of the glass.
You can kind of get a feel for it by imagining one of these mirrors being expanded to the size of North America. Well, if it were that big, then the highest bump would be 1 inch high, and the deepest valley would be 1 inch low. That's how accurate they have to be in order to work well in the telescope.
After the glass is constructed, formed, and measured, it is moved by airlift to a grinding station. Here, ceramic tiles and something like jeweler's rouge rub away the uneven surface. Then this completed mirror will wait for its 6 siblings over the next 3 years before they are transported to Chile. Martin hopes to be there for the construction of the telescope, but is still happy about what his job means.
If you're going to tell somebody one thing about what you do, it's that you make the biggest mirrors in the world. And I can tell you, you're looking at the biggest mirror in the world here.
For Arizona Cat's Eye, I'm Sarah Rogers.
So how is technology revolutionizing astronomy and solving some of these problems that telescopes have unavoidably due to the Earth's atmosphere? One method is called adaptive optics, where basically we can use clever mirror design and flexible mirrors to change the mirror shape to compensate for atmospheric turbulence and allow telescopes to approach their natural and fundamental diffraction limit. Now, these changes to the mirror are not done to the primary mirror because it's too large and heavy, but they're done with the secondary mirror, which is also used to reflect back light down through the central hole, and it's a smaller mirror. So for an 8.4 10-meter mirror, the secondary mirror is typically less than a meter in size. So it's the secondary mirror that has adaptive optics, and you can see in this before and after pair of images how it reduces the image size by taking out the blurring motion of the Earth's atmosphere. Here you can see at 2 microns how it affects an image of the center of our galaxy when the adaptive optics is turned on or turned off. Adaptive optics is now a standard system at all the world's largest telescopes. It could be used in the optical and the near-infrared. And you can see that in a dense field of stars like the galactic center, if you look how blurred these stars are without the adaptive optics, you would not count nearly so many, or close stars were just blended together. As you sharpen up the images, a large number of stars are visible, and you can see much deeper and much fainter. Here we have a triple star, and as the adaptive optics is switched on, you can see instantly that the very close pair at the center can be resolved, whereas without correction, impossible to see that there are actually 3 stars there. And this shows the jitter of a star caused by the turbulence in real time, and as the adaptive optics is switched on, you lock in on the core of the image, and you can see again a faint companion. Now below is a pair of images adjusted to be equal amount of light gathering time. One of them is taken from the Hubble Space Telescope, and one is taken from a ground-based telescope in Arizona using our adaptive optics. And I would challenge you to say which one is from the ground and which one is from space. The answer is the one on the right is from the ground. It's actually slightly better from the one from the Hubble Space Telescope. The point of this is that adaptive optics, the ability to cheat the turbulence of the Earth's atmosphere, has essentially closed the gap between ground-based telescopes and space telescopes, with the huge difference being that we can build much bigger telescopes on the ground and much cheaper than we could ever launch from space. And that's the end of this topic.